Lesson 14 takes us back to limits. We talked about limits, I don't know, lesson 10 or 11, somewhere in there. Okay. As I said, limits is one of our big three topics when it comes to calculus. It's limiteds, derivatives, integrals. Okay. So, we're going to talk about limits. These limits that we're looking at, I don't know, some we'll look at graphically, but we're going to look more at algebraically more than anything. So, okay, a function has a limit at a particular value of x if it has both a left and a right-hand limit at that value of x, and these two limits are equal. So when we looked at limits last, we looked at a left-hand limit, a right-hand limit, yes? If it's not specified to look from the left or look from the right, you're looking at the limit in general, which means it needs to meet at the same place coming from both sides. Okay, that's what that gibberish there is saying. Is that this function, if it has a limit, it has both a left and a right-hand limit, and these two limits are equal. Okay, that's what we're saying here. So the left and the right have to be equal. Now, with that in mind, that is also part of the definition of a continuous function. We use the word continuous quite a bit in calculus. And this is an example of a continuous function if it has the limit from the left and the limit from the right match. Okay? So as I said, if it doesn't ask, you need both sides to be the same. Now, find the following limits. If f of x equals x plus 6, then the limit as x equals 3 of f of x plus 6, which basically x plus 6 is f of x, isn't it? So if this is asking the limit as x approaches 3 of f of x, which is x plus 6. Thoughts on how to find that? I'm trying to think how much you guys know, and I'm not really 100% sure.
So we're trying to find the limit of x. We're trying to find the limit when x is approaching 3 from the positive side.
Not from the positive side.
Negative.
From both sides.
Okay, yes.
There's no, if it was a positive side, there'd be a little plus after it. If it was a negative side, there'd be a little negative after it, right?
So, in this case,
One option is you can graph it.
yeah, I was going to say graph it.
And for the beginners, we're going to graph it. But in all honesty, that's way too hard of work for this problem. Just saying. You'll see why here in a moment, okay? So let's make the connection. So if we graph this, f of x equals x plus 6. So I'm graphing x plus 6, right? Which you guys know x plus 6 is a straight line, right? mx plus b. I was just teaching this last period in Algebra 2. Now, we want as x approaches 3. So if I hit trace, I feel like it's kind of hard to see my calculator here. But as x approaches 3, so take trace and just kind of start moving over. Okay, 2.4, 2.5, 2.7. Are you watching your y values? Oh, and then I just went 3.03. 2.87 was 8.87. 3.03 was 9.03. What's the guess?
So it'd be 9.
It'd be 9.
So you literally just put the number you're approaching into the function.
Yes, it is sometimes that easy.
Sometimes it's always.
A basic limit is that easy though, okay? And if I had just typed, if I'm on, let's see, I'm on trace, and if I just type in 3, yes, you know, at the point, it equals 9, doesn't it? And that's the thing, because this is a straight line, I just need to know the value of that point. It's a straight line, it's a continuous function, so when it approaches x equals 3, it approaches whatever the y value is there. Does that make sense? Okay, so it is that easy that we're going to say 3 plus 6 equals 9. If g of x equals x squared plus 3, the limit as x approaches 3 of x squared plus 3. So this here is the limit of g of x. What do you know about x squared plus 3? It's a parabola, right? Is a parabola continuous?
Yes.
Yeah, it's one line, right? It's continuous. So because it's a continuous function there and just one, I use the word line. It's not a straight line, but you know, one piece. What do you think?
So, in this one, if I'm correct,
Mm-hmm.
9 plus 3, which is 12.
Mm-hmm. Plug in 3. 3 squared plus 3 is 12. Oops. And again, if I do graph it real quick, x squared plus 3, I've got my red parabola there. And if I do a trace here, now when I hit trace the first time, I'm on the blue. I think if I use my up or down arrow, it switches me to the parabola. But when I trace this over to the x value 3, oh, I'm actually going to be off the screen. It does let me keep going. But notice I'm right around 12, aren't I? If I type 3 once I'm in trace, it gives me 312. So we're approaching 12 from both sides. Now, okay, let's look at a few limits rules. Based on what we just found up above. So we just found the limit of f of x as x approaches 3 to be 9. And we found the limit of g of x as x approaches 3 to be 12. So the limit as x approaches 3 of f of x plus g of x. Well, the long of it is the sum of two limits. No, this is the limit of a sum. I forget which way to say it. So this is the limit of two things added together, right? Is equal to the individual limits added together. So the limit as x approaches 3 of f of x plus the limit as x approaches 3 of g of x. Sorry, I'll zoom in so you guys can see that a little bit better. So that's what that's saying. If it's a limit of f plus g, that's the same as saying the limit of f plus the limit of g, as long as everybody's approaching the same number, right? So can you guess how basic this is to do this? Nine plus 12? Because up above, the limit as x approaches 3 of f of x was 9, plus the limit as x approaches 3 of g of x was 12, and 9 plus 12 is 21. So that's the official calculus language, okay? What you need to walk away knowing is, okay, I can take the limit of two things added and rewrite it as two individual limits being added. Now, can you guess what that means about the next one? Yeah, you're just going to subtract them. It's the limit of f minus the limit of g, which means I'm doing 9 minus 12, which is negative 3. I know it's going to be a shocker. Limit of f times g. Yeah, means I can do the limit of f times the limit of g. And 9 times 12 is 108. Division, the limit of f divided by g, I can do the limit of f divided by the limit of g. Nine over 12 can reduce to 3/4. Okay. Continuing. The next portion asks us to graph this piece by hand. So, without a calculator, off the top of your head, Do you know what this graph looks like? By the way, we're missing a y. That should say y equals. Hopefully that's understood, but that's y equals x squared minus x minus 6 over x minus 3. So you know what that graph looks like? Exactly. We're going to get to a form where we can. What do you notice about that numerator? The top factors. X squared minus x minus 6 factors into two parentheses. X and x. We multiply to be negative 6 and add to be negative 1. Minus 3 and plus 2. We have x minus 3, top and bottom, so those factors cancel, which leaves us with what? X plus 2. Right, so leaves us with y equals x plus 2. You know how to graph y equals x plus 2, yes? What's the catch here, though? Because I can't just randomly cancel these x minus 3s and have nothing happen because of it.
Yeah, because there'll be a hole with negative 3.
Okay. When the denominator equals 0, it's either a vertical asymptote or a hole. If the factor x minus 3 did not cancel, it's a vertical asymptote. Because the factor of x minus 3 had another factor of x minus 3 to cancel with, it's not a vertical asymptote, there is a hole. So there's a hole at x equals 3. So meaning, if you graph this on your calculator, it's going to look like the line y equals x plus 2. And unless you know to look at it, you might not even see the hole at 3. Okay, if you traced or something, it's there, but you wouldn't necessarily know. So if I graph this, let's see, x plus 2. I'm just basically going to do like a first quadrant graph because that's really what, that's enough for me. There we go, the action. So we have okay. So y equals x plus 2 is a line that has a y-intercept of 2 and a slope of 1. So slope of 1 means I'm going to rise 1, run 1. Except what happens when I get to 3. I'm going to put a hole instead of a dot. Except you can't see the hole I put because it's off the screen. So paper and pencil wise, that's how I show a hole. On the calculator, depending on the view, you might be able to see a gap in the line. You're not going to see a circle, but you might see a gap in the line. Or you might not. So this is where we have to, and I know I taught this in pre-cal, don't just rely on the graphing calculator. Look at the equation and use what you know about equations. The fact that I see x minus 3 in the denominator means I know something's happening at x equals 3. Whether it's a vertical asymptote, a hole, something's got to be happening there. Okay? So that's what you've got to take that into mind. Are we okay with that? Okay. So, what would be the limit, before I move on to the next one real quick, what's the limit of this graph as x approaches 3? So as x approaches 3 right here, it's approaching the y value of 5. And that's the answer, 5. Okay. Does my graph have to officially exist there? No, this limit exists because both graphs are going towards 5. Okay? Yep. The left and the right, the two limits are equal. Now, I guess technically, this function would not 100% meet the definition of continuous because there's a hole. I guess it depends, yeah. You'll learn little nuances as we go about that kind of stuff. Okay. Algebraic example here. Evaluate the limit as x approaches 2 of x squared minus 4 over x minus 2. So, what are you doing? What? Okay. I mean, like up at the top of the paper, we learned that we can basically just plug it in, right? Okay, so let's plug the value in. We're plugging 2 in. What happens when you plug it in? 0 over 0. Unfortunately, it does not.
I knew that something like that happened, which is why I kind of threw it out there. I'm like, does that equal 0? I knew last year you hinted at the fact that 0 isn't always 0.
0 divided by 0 is not possible. Okay, 0 divided by 0. I mean, you can't divide by 0 anyways. I know 0 on top is always 0. 0 on bottom is undefined. But when you put zeros both places, it's a special case. So, okay. Plan A of just plugging the value in failed. We need a plan B. Now, yeah, you know, it was too good to be true that we could just plug the value in. Good news is it's not a horrible plan here. Before we graphed up above, what did you guys do? We factored. Well, can we do any factoring here? X squared minus 4, do you remember factoring that? X squared minus 4 breaks into 2 parentheses. Yep, an x plus 2 and an x minus 2. Does that sound familiar? Obviously, I expect you to know that for calculus, but this is your reminder as we get back into the math, right? If you haven't done it since last year, there's your reminder. Denominator is x minus 2. Oh, what do you notice? X minus 2's cancel. So now, it's the limit as x approaches 2 of x plus 2. Four. Plug the value in now. Plug in 2, and 2 plus 2 is 4. So similar to the last problem. On the last problem, if I said, okay, what's the limit as x approaches 3, and you tried to plug 3 into the original equation, you would have been stuck. Okay? We could not have plugged, I guess I have to zoom back out here. We would have plugged 3 into this equation right here. We would have had 0 in the denominator. That's a problem, right? Okay, we would have had 0 over 0. So, but once you factor, we would have had x plus 2. You could plug it in. Same type thing here. Now, is the graph actually going to exist at 2, 4? No, there's going to be hole, just like there was up above. Okay? So not horrible. Okay, but of course it can't just be always plug it in. We have to have other devices, and plugging it in doesn't work. Okay? Example 2. Limit as x approaches 3 of x squared plus 2x over x plus 1. What are your thoughts? Let's try plugging in, see what happens. Okay, if we plug this in, 3 squared plus 2 times 3 over 3 plus 1. I don't know about you guys, but I got an answer, right? It's not any crazy 0 over 0 business, so this one actually works. Could you have factored here? There was one small factoring piece you could have done. And you could have factored out a GCF on top and had x times x plus 2 over x plus 1. But did that factoring really do me any good? No, because nothing canceled. When the factoring is really beneficial is when something cancels and allows us to actually get an answer. So this is where, don't just assume, oh, I have to, I can't just plug it in. Maybe you can. But on the other side of that, don't just assume we can't plug it in, right? You can't assume either way. You have to be ready to look for options here. Okay. Thoughts on example 3? Okay, did you try? Okay, so if we plug it in, let me write this down for the notes, sake of the notes. Once we plug this in, we end up with 9 plus 18. Okay, so 27 over 0. I know, Ross just told me that, and just didn't remember it. Okay, so what's a plan B option? On top, x squared plus 6x both have a GCF of x. X plus 6 over x minus 3. Well, did that help any? Does anything cancel? Okay. We're not supposed to be looking at the graphs, but I want to show you what's happening because the denominator is 0. Okay? Because this will make it... Oh my gosh, my calculator just went to slow mode. Oh, the other piece of the graph must be off the screen. Okay. So, right here, we're looking as x approaches 3, right? What's happening at x equals 3? Because it doesn't cancel, it's not a hole, there's an asymptote. This one you can see is approaching down, yes? Let me try ZoomFit. ZoomFit is not always my friend. I like ZoomFit. I don't like ZoomFit. Yeah. Let's see. Is ZoomFit going to be my friend here? Well, okay. Kind of totally changes what the graph looks like, but it shows us what we need, yes? Because, so, as x approaches 3, from the left, where does my graph go? It goes down. We'll talk about that being negative infinity in another lesson. As my graph approaches 3 from the right, where does it go? It goes up. We'll call that positive infinity. Are positive infinity and negative infinity the same thing? No. This limit does not exist. And our clue was the 0 in the denominator. Not a 0 in both, but a 0 in the denominator only. That was our clue. Okay?
Oh my gosh, this was amazing.
Oh, shush. I'll show that clip another day. That's when the limit approaches infinity.
Oh. Yeah, because she's like staring at her tooth. She's got lipstick on her tooth, and she's like, "Wait, you can't be mean." And she's like, "Okay, what is this?" Aaron got a haircut that day, and she goes, "Oh, the limit does not exist." I watched the movie growing up so much.
I think I watched it with my sisters once, and the one part that stuck out to me is when she goes, "Raise your hand and victimize Regina George," and then somebody raises their hand and is like, "She doesn't even go here." For some reason, that whole movie, that's what I remember.
I usually show that clip later on the day when we specifically talk about limits as x approaches infinity. Because I think that's, if I recall, that's what it is in Mean Girls.
Yeah, I think it is.
Unless I was supposed to show it today and I forgot. But
I take it nobody called that one last year.
well, we usually talk about it, and I can't remember it's been a couple of years ago, someone says, "Oh, Mean Girls." And so I specifically looked for the clip because I haven't seen the whole movie. I've seen bits and pieces, but I specifically looked for the clip, and I was like, oh, that's a fun one to show. So, kind of like minions and vectors, you know. And you didn't miss you don't usually miss either. Okay. I was like, I don't even remember what it was. But.
Oh, wow, so we got to watch YouTube videos of Vector. Y'all went high.
Okay, example 4. Keep us moving. I'm sorry. I'm as bad as you guys. I know. Okay. I'm not laying the guilt just on you guys. Limit as x. Wait, that should actually say t. Sorry. And why should it say t? Because t is in the problem. We can't have a limit as x approaches 2 when there's no x in the problem. Okay. Just make it make sense, right? So it's a limit as t approaches 2 of t minus 2 over t squared plus 4. So what you doing?
So if you plug it in at 0,
Let's
just 0 theory, but maybe there's some calculation where it's not 0.
Okay, so if we try the plugging in, we get 0 over 8. And I'm laughing back there at Ross, who says in normal stuff, or however he said it, 0 divided by 8 is 0. The answer is 0. Okay, the answer is 0. 0 is a number, answer is 0. And could this have factored anyways? No, there's no factoring. Okay, example 5. Limit as x approaches negative 1 of 2x squared plus 5x plus 3 over x plus 1. Well, and here's the deal. You can tell the denominator is going to be 0. Now, if the numerator is something other than 0, it would just be a limit does not exist. However, did you guys try it? If you plug, you end up with 2 minus 5 plus 3. Yeah, so you end up with 0 over 0. So right off the bat, we know we need to go to plan B, which means I need to factor. Okay. Denominator is x plus 1. You want some reasoning from me? If there's an x plus 1 on bottom, I'm not trying to use the word has to be, but there is likely an x plus 1 on top, right? So I'm going to go with one of my factors is likely x plus 1. Now, work backwards with me. 2x squared would come from x times 2x. Does that make sense? 3 at the end comes from 1 times 3. All the signs are positives, so I'm going to say 2x plus 3. Now, can you do product of AC? Of course. Can you double check yourself if you're not quite convinced on my reasoning? Yeah. 2x squared plus 2x plus 3x, so there's 5x plus 3. Okay, so just, you made it to calculus. You've got the big brains. Some of this reasoning you can handle, okay?
I don't think that I have a big brain. Can you go through the product basic?
Yes, I can. Definitely will.
As you started to talk about how
Okay, let's review, because we talked about this the other day. So, product of AC is going to be, do we remember this form, right?
I remember you multiplied.
2 times 3, which is 6, right? We need a sum of B, which in this case is 5. What multiplies to be 6 and adds to be 5? Multiplies to be 6. Because they're both positives, okay, here's the hardest part. Because they're both positives, we're saying 2 and 3. What do we do with that 2 and 3?
So you have to put them where they fit best.
You split the 5x, right? You can split it into 2x plus 3x or 3x plus 2x. Whichever makes you happier. So 2x squared I carry down. I agree. I would do plus 2x plus 3x, right? And then the plus 3 we carry down. 4 terms, we split it in half. GCF of the first half. They both have a 2 in common, they have an x in common. When you factor out 2x, left with x plus 1. 3x and 3, I'm going to factor out a positive 3, which leaves me with x plus 1. X plus 1 is a common factor because it's a matching parentheses. My other factor is 2x plus 3. Does that sound familiar now?
Yeah, I remember how to do it. I just jump in your logic up there.
Didn't like that?
No.
That's fine.
Not like that.
Okay. I know I have more of a chance with you guys liking that logic than 2 years ago when you were in Algebra 2. Then everyone resisted me. Now maybe some of you are following that logic. You know. Okay. So, finishing this problem up. We have a lovely nice x plus 1, right? So the limit, if I rewrite this, fancy notation, limit as x approaches negative 1 of 2x plus 3. And now I'm ready to say 2 times negative 1 plus 3 is 1. Yep. And keep in mind, guys, you can check any of these you want with a graph. But what you can't be doing is you can't be relying on using the graph to find them right now. Okay? That's just not an option. Okay, example 6. Have we already tried? You get 0 over 0, so we'll just nix that one right off the bat. Okay, I need a plan B.
So the top does factor, right?
It does.
Into x minus 2, x plus 2, x plus 2.
No.
No, I think they're all x.
So they're all negative.
What are you saying, Abby? Not perfect square, it's perfect cubes. So this factors into a binomial times a trinomial. When it's the difference or sum of cubes. Okay. It's written in your notes as like the f cubed minus s cubed business. Okay. So, first of all, just take the cube root of both pieces. The cube root of x cubed, x. Keep the same sign. So it's going to stay minus, and the cube root of 8 is 2. Got that? Now, trinomial. The first term is always okay. Look, I don't look at the original problem now. I look at my binomial. The first term here is this first term squared. So if I take, in this case it's an x, so I take that and square it, it's x squared. The hardest one to remember is the middle term. You're going to multiply these two pieces and use the opposite sign. So if I multiply 2 times x, that's 2x, and the opposite of a minus is a plus. So plus 2x. And the last term is this piece squared, and 2 squared is 4. And this last piece is always a plus, positive. So you can think, okay, what's negative 2 squared if you want, but it's a plus 4. And it's important to get that piece right or you can't finish this problem if you want to get technical here. Okay, so what happens?
So it's x squared plus 2x plus 4. You get 4 plus 4. 8 plus 4.
Okay. I already wrote mine for officialness. Limit as x approaches 2 of x squared plus 2x plus 4. Notice I used parentheses around a quantity with multiple pieces, just indicating the limit goes with the whole thing, not just the x squared. But yep, plug them in. 2 squared plus 2 times 2 plus 4 is 12. Okay. Thoughts on, no, example 7. Okay, so you've already figured out the first part. Plugging it in gives you 0 over 0. Okay, what are your other thoughts?
If you square the parentheses outside, you get like 9 plus x squared minus 9. So the 9's cancel, right?
Well, let's talk about this. When you square 3 plus x quantity squared, please remember you have to do 3 plus x times 3 plus x. And you have to FOIL it, which means it's very important to know Ross left out a term, right? Okay, and we can go this direction. So, if we FOIL out 3 plus x quantity squared, that's going to be, I like the 9.
Yeah, it's x squared plus 6x.
Okay, I'm going backwards, so I'm writing 9 plus 6x plus x squared, but I'm perfectly fine. Yep. So 9's cancel, and I have the limit as x approaches 0 of officially x squared plus 6x over x. When we talk factoring and GCFs, we can factor out the GCF of x, so the limit as x approaches 0 of x times x plus 6 over x. And yes, that does allow an x to cancel. So we have the limit as x approaches 0 of x plus 6. So all that work, and yes, it's 6.
And then since the x canceled, how would there be a hole there in here?
Yep, there'd be a hole.
Would be 0.
It'd be a hole at x equals 0. So it'd be a hole at the point 0, comma 6. I mean, that's what most of the ones we've been looking at, the hole is at where the limit is. That's the idea. Okay, check your answer for number 14.7 by using your calculator, which means, what are they saying to do? We're going to graph it. So, let's see, parentheses 3 plus x, parentheses squared, minus 3 squared over x. I'm going to do zoom 6 because I had that silly zoom fit last time. Now, you look at your calculator, but looking at my calculator, I know it's kind of blurry there, but can you see a hole just looking? Now here's what I will say. Maybe I guess. I don't really feel like I can see one. If I zoom in, it's like if I put my cursor up in that area and zoom in around it, I might be able to. Because sometimes the more you zoom in, the more you can see it. I don't really feel like I can see it, but here's the other thing. If you hit trace, my trace brings me up to 0, and it's 0, and then y is blank, which means it doesn't exist at that point. Because if I go left or right, I have y values. But that just indicates there's a hole there. Okay? And every calculator works a little bit differently. But yeah, that's just checking. That's just, okay, look at the graph. There we go. There is my, you guys can't see what I wrote. There's my fancy graph. Nothing too crazy, but. And somehow we're down to 10 minutes. We definitely socialized too much today. We should have had plenty of extra time in this one lesson, but that's all right. I find myself guiltier of that in calculus just because it's a small group of us. And
we're so fun.
I keep graphing mine. I get a parabola and a separate line.
Are you
only me, so I wasn't gonna say anything out loud.
Hold on. Let me stop this before I forget. You guys do have a homework to get out.